Okay, so this is from the Monday class. If you were here, or hopefully you watched the video, all these are addition reactions to alkenes. So all of chapter 8, if we just do this general thing, that's going to be connected. All right, there's going to be some reagent. I don't even want to say the reagent is XY, but we're going to add something. We're going to break the carbon-carbon pi bond. We're going to add something to each of the two sp2 carbons. Right? X and Y could be the same thing. They can come from the same reagent. They can add on the same side. We're going to call that a syn addition. So one of the last reactions I put on the board Monday was syn dihydroxylation. So we put an OH on each of the two carbons, and the two OHs come from the same side. Right? So that's basically in all of these reactions, up until this one, the anti-dihydroxylation, I went through the mechanism on Monday. We might talk about it some today. But the syn dihydroxylation with osmium tetroxide, I did not do a mechanism. You don't have to know that mechanism. But for all of these, what you need to keep in mind, you need to know the reagents. And I said this on Monday, for this dihydroxylation reaction, really the only reagent here I care for you guys to memorize is osmium tetroxide. And you need to know what it does. So if you see osmium tetroxide and a carbon-carbon double bond, you're going to put two OHs on the double bond from the same side. Yeah?
Could you draw the structure of osmium? I forgot how you say it.
Osmium tetroxide. That's it. So, as you sort of group these reactions out, there's kind of a summary, I call it a reaction flower at the end of the chapter. It's like got an alkene in the middle. We all use methyl cyclohexene in this one, unfortunately. You need to be able to extrapolate that. I'm going to have a worksheet out today that will give you different alkenes to work with. But methyl cyclohexene is nice in that it gives you the methyl to show sort of which side things are on, or where, actually what the methyl does is let you figure out where a nucleophile might attack, the more substituted, the less substituted carbon. A ring is nice because it's easier to see, right? So if the alkene's in a ring and you get syn addition, the two groups are going to be cis. If you get anti-addition, they'll be trans. Yep.
So for all addition reactions, does it attack the most substituted?
No.
Oh.
Sometimes you have to know for each one, like
Okay.
how it goes. Okay, so the new reaction today is actually, we're going to do two reactions today. One will fit this paradigm, one will not. All right, so the one that doesn't, let's do that first. This is called an ozonolysis reaction. This is a fun reaction to do. And ozone should be everybody's favorite molecule. Like if you're just talking about kind of a generic, small, everyday molecule. How many of you grew up in a house where someone put an ozone generator for air purity? Anybody have an air purifier in the house? Just an air purifier. It might actually be an ozone generator. So, all right, let me do the reaction here. So O3, and then some sort of reductant. And again, what I want you guys to focus here is the O3. Right, so the ozone. And this is going to give you easy, right? You guys all intuited that as soon as I said ozone. All right. So normally, really the math sucks. My teaching style has been hurt by the math. There's a lot of times I'm kind of smiling knowingly at you, and it's clearly a joke. This looks like a wild reaction, all right? And it is a pretty wild reaction. I'm not going to ask you the mechanism for it, but I'm going to tell you how to figure it out. And if you look at this, if we number these, let's start with quaternary sp2 carbon, right? It's a 6-membered ring, so if we go counterclockwise around the ring, carbon 1 is, bonded to 2, 3, 4, 5, 6. So 1 and 6 are double bonded. If you put these in over here, it goes like so. All right, so we break, in the ozonolysis reaction, both carbon-carbon bonds break. All right, so we're going to just slice through both of these carbon-carbon bonds. This is the only reaction in chapter 8, really probably the only reaction in the textbook where you break a double bond completely apart. And so let's imagine doing that. Do kind of a thought experiment over here. All right, so I'm going to do the ozonolysis reaction. This is a visual. You have to watch me do this. All right, everybody watching? So ozonolysis, you're just going to break through both of these bonds. Well, then that leaves the 2 carbons then are down 2 valences. They're only bonded to 2 things. Carbon's going to be bonded to 4 things. You've got a whole bunch of oxygen here, and so you just come in and replace those 2 things with a carbonyl. All right, so you break through the carbon-carbon, sigma and pi bonds, and then each of those carbons winds up double bonded to an oxygen. That's it. All right, so I unfolded it here. Right, this is the same molecule as what I drew as the product. Right, so you remember you can rotate freely around the sigma bonds. So you just rotate around all these sigma bonds to straighten the chain out to get what is drawn as the product. So this reaction happens, like I said, ozone maybe should be your favorite molecule. Here's one of the resonance structures for ozone. Probably in high school or general chemistry here at Wake, when you guys first encountered resonance structures, ozone was probably one of the ones that you saw. So this negatively charged oxygen can make a pi bond here, kick these electrons to make that oxygen negative, and so the 2 O's on the ends are equivalent. And then this reaction does that's the mechanism for the reaction. And this is really an aside at this point, but why that first step of the ozonolysis works. If you look at benzene, so in Orgo 2, you're going to see benzene, you're going to talk a lot about benzene chemistry. Benzene looks like it ought to just be 3 alkenes in a ring, right? So I've been doing all these examples with the 6-membered ring with an alkene in it. And so it would be very logical for you guys to look at benzene and say, well, that just does all these chapter 8 reactions, it just does them 3 times. Here's the thing though. Benzene doesn't do any of the chapter 8 reactions. So benzene turns out to be way more stable than the Lewis structure suggests. All right? The Lewis structure suggests it's just a 6-membered ring with 3 alkenes in it. Quantum mechanics winds up making benzene way more stable. And I don't have time to go, I mean, it's not even time. It's beyond the scope of going into it right now in the alkene chapter. But depending on how Dr. Jones teaches Orgo 2, if you take Orgo 2 next spring, sometimes we start with benzene chemistry and sometimes it's about halfway through the semester. But anyway, when you get there, she'll go into this in some detail. But the quantum mechanical feature that makes benzene way more stable than it looks like it should be is that it's got 6 electrons in a continuous ring. And so if you look at this ozone transition state, right, this is one mechanism. We have 2, 4, 6 electrons in a ring. So the transition state for this reaction is a lot lower than you'd expect it to be. Again, I'm not going to ask you this mechanism, so you don't really have to know this. This winds up giving you You guys aren't gonna be able to see this at the back. Everybody write this down right now. That's like a really important thing going into the exam. Going into exam 3. Benzene is not an alkene. It's got an ENE at the end, again, because the folks that discovered the structure of benzene saw those were double bonds, didn't know any quantum mechanics, they were about 40 years too early, named it an E. But those double bonds are not alkenes. Okay, so I'm going to erase that and talk about the ozone now. All right, so this mechanism, you end up first, right? It is a reaction of the double bond. So the pi bond breaks, you get 2 bonds to oxygen. And so at this point, it looks like an addition product. It is an addition product. And then you get kind of a crazy mechanism. I'm not going to go through the arrows for it, but you wind up breaking you break this carbon-carbon sigma bond and rearrange the oxygens into what's called an ozonide. Again, I can't emphasize this enough. I'm not going to ask you to do this on a test. That mechanism, there's still some debate about actually how that process goes from the initial adduct to the ozonide, how that actually happens. There's some debate. What is really well known is that ozonide is very explosive. Okay, so if you do one of these ozone reactions, and at this point, at the end of step 1, this is the product at step 1. Right? If you rotovap that down and concentrate it, there's a very good chance you'll blow your rotovap up. So don't do that. The other thing is, this is a really fun reaction to do. Have you guys run reactions in lab? I know you made plexiglass this week.
Yeah.
It's like a reaction. But it's all color. You see a phase change. You go from liquid to solid. That's pretty cool. Here, ozone is this really lovely blue color. And you get ozone when you pass an electric charge through air. So a really high voltage electric arc through oxygen will produce ozone. So you smell ozone, everybody talks about the smell of rain. Often what they're referring to is the smell of ozone from lightning. So lightning passes through the air, generates some ozone, you get that smell. There's also a smell from storms that happens in the soil that's really cool biochemistry. But anyway, you can make ozone that way. We have a big machine that makes ozone. You bubble air through an arc. The gas, the air winds up carrying a few percent of ozone that goes into the solution. As long as there's an alkene there, right, the alkene reacts essentially immediately with the ozone. Once your alkene is consumed, the ozone builds up in solution, and it turns into this really lovely blue color. All right, about the color, there's 2 or 3 disposable masks. Some I noticed, the disposable masks don't all have the same blue color. Looks like they should, but they don't. I think your blue is you can look at it later. I think your blue is the most ozone-like of the ones I see. It's this really nice blue color. I don't know, I think it's very pretty to see that. And it's always fun, I think, when you can use the reagents themselves to tell when your reaction's done.
Wait, is it a gas or a solid?
Ozone's a gas.
Okay, so the gas itself is that blue.
Yeah. Well, when it's in solution. You can only see the color when it's in solution. There's a lot of gases that have color, but they're so, you remember Beer's law, right? So color has to do with concentration. And if you have just like 1% of ozone in the air, you'll smell it. I mean, you'll smell like a part per million of ozone in the air. Really, if you have 1% of ozone in the air, you're in trouble. So the way ozone works to be an air purifier is by killing bacteria and fungus and stuff like that. Right, so anything that's toxic, that's usually a dose thing. So if something will kill bacteria, like bleach kills bacteria. You drink enough bleach, it'll kill you, right? The only reason a little bit of bleach in the air doesn't kill you is you're way bigger than a bacteria. Okay, anyway. Ozone's a gas. If you dissolve it in solution, you can see the color usually. Anyway, then the last step here, step 2, and again, I'm not going to go through the mechanism. It's a little easier to see, but it's no big deal at this point. Step 2, cleave the ozonide down to the carbonyls. Okay, so ozonolysis. Carbon-carbon double bond, rip through both of the bonds, replace the two bonds on each carbon that are lost with oxygen.
So if it's not in a 6-membered ring and you have an alkene, will the molecule always split?
Yeah. So let's do one where that's important to know. So if you don't have, if it's not a ring, all right, predict the product of that reaction. Yep.
So, why is there not a hydrogen on the left side of the product? Because that would make it 7 carbons, right?
Hydrogen on the left side, that's the methyl.
Then on the product.
Right, here,
Oh, I see.
that methyl. So I'll number that as A.
I'm just wondering, why isn't that counted in the carbon chain?
I didn't put a number on it.
Oh, okay.
I mean, it's a
That's all.
6-member. Yeah, I was just, yeah, sure, it's in there. Like, if you had to name this, you'd definitely have to include that methyl as being in there.
And it would be a 7-member.
It would be a, yeah, it would be a hepta something.
Okay, I just wanted to make sure I wasn't.
Let me see if I've got that product in the. Okay. All right, so again, over here, yeah, so if you were wondering about this methyl, when you rip through the double bond, carbon 1 becomes a ketone because the alkene carbon 1 in the starting material has 2 carbons on it. Carbon 6 becomes an aldehyde because one of the things bonded to carbon 6 in the alkene has an H on it. All right, another 30 seconds or so on the ozone reaction on the left, right. The other thing there is my numbers aren't meaning that I'm not doing nomenclature with those numbers. I'm just keeping tabs on what's where. Right? So really what I just drew is the reverse. You would number those the other direction. All right. You ready? Okay, so again, like I said, we're just going to come in here and we're going to cut through the carbon-carbon double bond cleanly. Both bonds are going to break. And so I think this is what you were asking. This means, in this case, because the two sides of the alkene are not connected to each other otherwise, right? They're only connected through the double bond at 3,4. That means you're going to split into 2 molecules. All right, so we're going to get that. Okay, so 1, 2, and 3. Carbon, the bonds we're going to break are between 3 and 4. So 1, 2, 3 all stay bonded together. 3, instead of being double bonded to a carbon, will be double bonded to an oxygen. And then the other side, we're going to get a ketone. This is going to be that. So 4 becomes a carbonyl, double bond to an oxygen. 5, 6 stay the same. And again, right, benzene doesn't do anything here. Benzene doesn't do this reaction. It doesn't react like 3 alkenes. So if you went in here and treated this like 3 alkenes, you'd expect to break through there, break there, break there. That's not what happens. Yep.
What if you have 2 double bonds
Then they would all break.
They would all.
Yeah. So that's, again, talking about gas, this is really important for the next reaction we're going to look at. It is really hard to control how much gas you have. That sounds, I don't mean that in a biological sense. It's hard to control the amount, right? If I'm using a liquid or a solid, I can weigh out 20 milligrams of a solid, I can pour out a milliliter of a liquid. It's really hard to control the amount of gas you add to a reaction. And so typically, like I said, this reaction is done in such a way that you just bubble ozone through it until everything that can react reacts. There's no way to go into it and just ozonize one alkene. So if you have 2, 3, 4 alkenes in a molecule, they'll all go. Yeah, so you could imagine doing let's say you ozonize this alkene. That's what you'd end up with. You get 4 molecules out of this, right? We'd break through here. So this carbon would have 2 methyls on it and a carbonyl. Break through, that carbon would be a carbonyl, that carbon would be a carbonyl. Right? We'd slice through there. So that's the middle molecule. With the carbon with the phenyl ring on it, slice there, you'd get a ketone. Out here, slice through there, that would become an aldehyde. And then the CH2 out at the end would just become formaldehyde. All right, so every alkene is going to react when you do this. Yeah.
This may be like a very ignorant question, but where does the third O go?
Where does the third O go? It's a great question. It goes to, so this step 2 is either dimethyl sulfide or zinc. All right. So let's say it's dimethyl sulfide. It's a little easier to see this way. The reaction starts with this, all right? And one of the byproducts that you get is that,
Okay.
right? So the dimethyl sulfide and the zinc, it's a little harder to see how the zinc does this, but it does. That's a reducing agent. And so if something's a reducing agent, it has to get oxidized.
So that's why it's not represented there.
Yeah. No, that's a good question. All right. That's ozonolysis. That's oxidation of an alkene. Next reaction will be reduction of an alkene. I'm going to do that on a new video.